everyone. So this will be another Legion week. And so today I want to talk some more. So if you remember last time, we were talking about, effectively how we do analysis on, these individual views over here, looking at how do you record dependencies for copies and tasks and other things on physical instances that are being used on each of these on these individual views over here. But I think today what we're going to do, we kind of finished that up the last time. So what we're going to do today is to start transitioning over to this part of, talking about the various kinds of types of views that we support in Legion, and actually start looking at collective views, how they work, and how they're used to effectively do more efficient analysis for things where we know that tasks are using the same logical regions as part of like index-based task launches and stuff like that. So today we're going to talk, talk more about collective views, the two kinds of them, replicated views and all reduced views, and also talk about how we do analysis with them, and how to think about them moving through the pipeline of Legion operations and stuff like that. Okay, so to refresh everybody's memory, the idea of collective views, we've talked about this in various contexts in Legion meetings and League A meetings and stuff previously, but just to remind everybody, there are cases now that we see a lot today where effectively you have maybe one index-based task launch where several of the tasks, the point tasks inside of the index-based task launch are using the same region, right? Like you might have one index-based task launch where two of these points are reducing to R0 and two of the points are reducing to R1. Right, and then you have some other index-based task launch that comes along later where, two of these points want to read R0 and two of the points want to read R1, right? And so you can have these cases where multiple points in the same point task are operating on the same logical region, whether they're doing reductions or read-only. Effectively, they're both going to be mutating the state of that particular, or accessing the state of that logical region, collectively. Right, and so what we want to do, right, as we're going through the analysis pipeline, right, like especially in the physical analysis pipeline, if I come back to this slide up here, right, like, it's possible, and certainly the case like before we had collective views, that each of those points that were doing the same analysis for the same logical region in the same index-based task launch could all go through and do all this stuff themselves, right, and that would work perfectly correctly. But it would often incur scalability bottlenecks, right? Because effectively what would happen would be that, multiple points would have to do a physical analysis, traverse like any equivalent sets associated with the logical region, issue any copies to their particular instance that they're needing to update, right? And then do their registrations and stuff like that, right? Now, in many cases, you can actually deduplicate some of that work. If you actually know that, several of the points inside of the same index-based task launch are actually going to be using the same logical region, right? Effectively, we don't need both of those points in this, in like both P0 and P1 to do the same analysis on the equivalent sets, right? Like we should be able to do it with just one of them doing that analysis, right? And updating the equivalent set with the name of a new collective view that represents maybe both of the instances that are being accessed, by these 2 point tasks, right? And so the idea of collective views is effectively to allow us to deduplicate some of this work as we go through these stages here. In particular, these stages with with updating the equivalent sets to find any copies and effectively be able to issue copies, to or from any collective views. Right, and then we actually do issue the copies, right, in the copy fill aggregator stage, right? We should be able to actually make those copies much more efficient if we know we're doing copies, between collective views. We should be able to use algorithms that are much more asymptotically efficient in terms of moving data between different instances and different places. Ultimately, when we get down to this stage, though, the instance views, we're still going to have to do the same. Every point task is going to have to register itself as a user of like each of the physical instances, right? So that part doesn't get deduplicated. But effectively, a lot of this work up here is going to be deduplicated. So let's actually take a look a little bit at what this picture is going to look like in the case of collective views. And then I'll start trying to tie this back to the code so you can actually see how this works in practice a little bit more. Okay, so in the case of like this index-based task launch that we had here, right, where effectively we had, 2 points that are using the same logical region here and 2 points that are using the same logical region here. The runtime doesn't actually know where those, where those matches are between those various different point tasks. And so the first thing that the runtime has to do, right, anytime that that you suspect that this might be happening, right, and for everyone that hasn't used collective views before, the hint that this is happening, that there's some points in your index-based task launch that are using the same logical region, that hint comes from the mapper, right? Effectively, there's a way to tell the runtime, hey, I think that my index-based task launch is doing some collective behavior with the various points using the same logical regions. Please go and check for that, right? And the mapper can be wrong, right? Like if there isn't actually any collective behavior, nothing bad is going to happen. You may pay a little performance penalty for the runtime doing the check to see if it can find any matches between the various point tasks that might be using the same logical regions. But it will not impact your correctness at all. So like you can safely ask the runtime to do that all the time if you wanted to. It just might make your physical analysis a little more expensive, but it's going to work correctly no matter what. So effectively that hint comes to the mapper, and when the runtime gets that hint, effectively what it's going to do is going to take an extra stage of the physical analysis to effectively do this parallel rendezvous across all the point tasks inside of your index-based task launch, and check to see which of the points are using the same logical regions. And when it finds some matches between points that are using the same logical region, what it's going to do is create a collective view to represent all of the instances that these points are matching. So like even though these 2 points are using the same logical region, right, they might be mapping to actual different physical instances, right? So like this might be mapping to GPU 0 and this might be mapping to GPU 1, right? They create different instances in those frame buffers. Right, but we're going to make one name to represent both of those instances, one view, one collective view that's going to represent, both of those instances, right? And once you've got that one name, we're going to send that back out to each of the analyses, right, for each of these 2 point tasks. And exactly one of those analyses is actually going to go and then update, each of the equivalent sets, for actually, doing any copies or recording that this is a new, valid copy of the data and so forth in those equivalent sets. Now, the thing is, it doesn't have to be like the same, like in the case where you actually, coming back to this picture up here, in the case where your analysis might actually need to talk to different equivalent sets to, right, for you have multiple equivalent sets representing this logical region, right, then it might be the case that, this point task updates some of the equivalent sets and this point task updates some of the other equivalent sets. But exactly one of these analyses will touch each of the equivalent sets for the logical region R0, right? And so we're going to look at how that code works, effectively how you guarantee that each one of those equivalent sets get updated by exactly one physical analysis and issues any copies, right, through that. And then after you've done your equivalent sets updates and you've made your copy flow aggregators and issued any copies out to these collective views, right? Then effectively there's another rendezvous that happens just between the points, sharing a same collective view, right? And that's effectively to establish that they've issued all their copies and all their copy effects, like the copies have registered themselves as users on all the views. Right, at that point, then each of these point tasks can go and do their local registration on the actual like materialized view that actually represents the instance that they're actually going to be using. And we'll talk about why this sort of rendezvous here is necessary. Notice that this one is not across all the points, right? This is only across points that are sharing the same collective view, right? So like this rendezvous here is across all the points in the index-based task launch, right? Because we don't know which points are sharing the same logical regions. Right, but down here, this rendezvous is only going to be between the points that are sharing the same collective view. So that's independent of what these other points are doing over here with R1 and R2, right? They've got their own collective view that they've made for their instances because they're operating on a different logical region, right? And so they don't have to necessarily synchronize with all the other points, before doing their local registration on their instances that they're actually going to be using. Okay, So today we're going to try and tie some of this into to the actual code to make it clear like how some of this stuff is happening. And we're also going to hopefully, look at some of the patterns of different kinds of efficient copies that we can do with collective views once we know that we're actually issuing copies between, between views that, that have different numbers of instances in them, right? Where maybe not all views have exactly one instance of them anymore. Now we might have like 1 to n cases where you might be doing a copy from a single view, out to a replicated view of many instances, right? And so you can build like a broadcast tree of copies to do that efficiently. So we're going to look at some of those today, hopefully, as well. And that's really the motivation for this, is to be able to do this kind of analysis and generating of copies much more efficiently than you could if you had to analyze each one of these points individually and stick them all as users in the equivalent, or all of them as views in the equivalent set, and not be able to analyze them efficiently. Okay. Any questions before we start looking at code to actually try to tease some of this apart and look at how this actually works? Okay, not hearing any questions. All right, let's take a look at some code. Okay, so actually, let's start with this part right here. So how does this happen, this parallel rendezvous to match regions to find or create collective views? So there are sort of 2 ways that this can happen. And let's do the most common way first, the way where we get a hint from the mapper. Let's see if I can remember the name of the. There we go. Okay, so we've looked at this method before in a previous lesson, right? So this is effectively the call that gets done from any operation that needs to do an update analysis, right? One of these update physical analysis, and we've looked at this update physical analysis before, and you remember that its responsibility is to effectively go through and talk to all the equivalent sets, for a region requirement, and issue any copies that need to be updated, for that particular region requirement to bring it up to date so that the operation can use it, right? And then register the region requirement for that particular task or copy or whatever it is, as a new user of that particular instance that it's being mapped to, right? So we've looked at this analysis before, and you'll remember that has several stages. Right, we've looked at perform traversal, how that traverses over the equivalent sets and stuff, and how perform remote can send messages to equivalent sets that are not local to our particular node, right? And then performing the updates or actually issuing any copies and so forth, right? So we've looked at some of these stages before, but one stage that we haven't looked at is this one that happens right at the very beginning after you make one of these update analyses. And effectively, what this stage does is this convert views stage, right, is the very first stage of any one of these physical analyses, right? And what it says is, we know that we're going to be mapping, this logical region to a particular physical instance, but we need one of these view objects, right? Effectively, we need to convert our name of our physical instance into, wrong slide there, into one of these view objects to represent that particular view. And it's probably going to be one of these instance views because it's actually a physical instance and not any one of our lazily evaluated things, right? So effectively, we have to do this conversion. And each task context maintains one of these mappings. But in the case of collective, rendezvous, we might actually need to do some checking to see, are we using the same logical region as any other points in our operation? And so you can see there's actually this parameter here, collective rendezvous. And that actually comes through from the caller, right? You can see that gets passed in here as a parameter from physical perform updates. And actually, if we go look at, where this method gets called, let's actually find it over here in the, where tasks call it. Physical perform updates. Right, and I think we actually want physical perform updates and registration. Yeah, this is the special case for where we have exactly one region requirement. Okay. Right. This is the output case. Sorry about that. Right, you can see this parameter here, check collective. So let's actually see where that comes from. So this is the parameter that's actually saying whether we're going to check for these collective rendezvous between all the point tasks inside of our index-based task launch. And you can actually see check collective here is done on this binary search on this list of check collective regions. And, I'm not going to trace it all the way back for you here, but effectively that check collective regions is directly coupled to the mapping interface. And so if you look at like map task here in the, right, you can effectively say there's, let's see, where is it? Trying to remind myself exactly where the check collective regions are here. Maybe somebody who's used this interface recently can remind me. Yes, we put it on the task options. I forgot that we did that. Here we go. So effectively, that comes directly from this, set of region requirements that the mapper can give us a hint to say effectively that there are collective regions in this particular index-based task launch, right? And so that's how it gets piped through that sort of hint all the way down to the physical, to this update analysis. Ooh, I went too far here. Right, and so that gets passed into this convert views call. So let's actually see what happens when we call convert views with this this collective rendezvous parameter here. Where's legion analysis? Here we go. Okay, so you'll notice we're in the registration analysis class. This is a base class for update analysis, right? So effectively this is sort of an abstract base class, right, that has some of the methods that are generic across several different analyses that all need to perform registrations. But an update analysis like the type that we're looking at before is a kind of registration analysis. So this is the method that gets called when you call convert views. And right, here's our collective rendezvous parameter. Now, in the common case, in the case where we're not actually given this hint, right? So you can actually see that this is actually, there's some stuff here for handling cases with atomic privileges and stuff. Most of those you can skip. Since atomic privileges are not used particularly often, but the actual conversion of the views actually happens down here at the very bottom, and you can see there's several cases here, right? And so the first case that we get is actually this case where the user has given us this hint, and we're going to invoke some method on the operation to actually do this parallel rendezvous to convert these collective views, and we're going to go take a look at that. Now, there are other ways that you can end up calling, that parallel rendezvous on the operation class to actually try to do this convert collective views. And that can happen in cases where, maybe the mapper hasn't hinted to us that, it needs to do a collective rendezvous, but we actually know that there is some collective behavior. Say, for example, if you're doing, an attach operation in a control replicated context, right? That replicated attach op is going to know that, you're trying to do an attach for the same logical region across all the shards. Right, and so that would be another case where you might come down this path here to actually do this sort of parallel rendezvous, and actually do this convert collective views call, which we're going to go look at. And then down here at the bottom is actually the case where there is no collective behavior between all the points in the index-based task launch, right? And effectively in that case you can go straight to the context and say just take each of my individual view instances that I want to access, and get directly the individual view that corresponds to my particular instance that I'm trying to analyze here, right? And so we only do this collective rendezvous case where either the mapper has hinted to us that we're actually going to be to potentially have this behavior, or in the case where effectively the runtime knows that there's some special behavior with control application that's actually going to enable us to do a collective rendezvous to actually do this analysis. Okay, so let's actually see how we do this parallel rendezvous to try and find collective views on a particular operation. So this convert collective views method is actually a method that comes from a base class in Legion Ops. Let's see if I can find the right. Here we go. So let's actually find this method here. So here's the convert collective views method. There's actually this is probably the one that I want, I think. Yeah, because this is the, it's a special overload for that one. Point detach. Here you go. Okay. So you can see there's actually a sort of a mixin class here, right? You can actually see this is a templated mixin class that operations can use if they're going to be a kind of operation that can be a collective view creator and effectively be able to do this parallel rendezvous. And the reason for this is we actually want to abstract this over lots of different kinds of operations, right? We want to do this parallel rendezvous sort of a generic way, and there are lots of operations that might need to do this parallel rendezvous to check to see if there are logical regions that are, are the same across multiple different point operations inside of them, right? And so effectively, this is a templated class, right, that effectively, that will extend any operation that builds off of it. And it's going to provide this implementation of convert collective views. And there's a lot of parameters here that that are getting passed in here. Most of these are actually out parameters. So you can see everything that's like a reference, whether it's a pointer reference or a reference here, those are all out parameters. They're going to get passed back out. Everything above here, that's either a normal pass by value parameter or a const reference, right, is going to be an input parameter. We'll take a look at this in just a moment, but let me finish showing you, where this collective view creator, it's actually going to show up in a lot of places, right? So if we look at what extends public or collective view creator, right? So we've got index attach operations, index detach operations, right? They're both examples of collective view creators here because they both need to do this parallel rendezvous. If we actually go look at Legion.task.h, we can actually see that there's more stuff over here that's a collective view creator, right? So effectively anything that's a multitask, right? Whether that's an index-based task launch or a a slice task, right? They need to be participating in this because they might end up having this method called on them. So effectively, this you can see multiple different operations whenever you see this collective view creator, sort of inheritance pattern here, right? That's effectively adding in support for the ability to do these parallel rendezvous between points to effectively be able to detect if there's point tasks that are using the same logical region. Okay, so let's actually talk about this this convert collective views method here. So let's look at these parameters because it helps to understand what's getting passed in here, right? So first thing that's getting passed in, this is the region requirement that we're doing the parallel rendezvous on, right? So if I came back to my little example here, right, it's possible that this little example here, I've given each of these tasks exactly one region requirement, right? But different tasks often have multiple region requirements, right? And you might actually want to do parallel rendezvous on different region requirements at the same time, right? So the mapper might hint that region requirements 1 and 3 are the ones that it wants to check for parallel, or for collective behavior on, right? And so you have to do parallel rendezvous, in parallel for each of those different region requirements. So the first thing that we pass in here, is effectively a region requirement index to say, so we can disambiguate between these parallel rendezvous that are going on for a collective view creator, for different region requirements. There's another parameter here, which is the analysis index. This is mostly irrelevant for tasks, but for some things like detach operations, they might actually have multiple analyses that they need to do. So for example, they might need to do an update analysis to issue any output copies, and they might also need to do a filter analysis to remove names of instances and stuff like that. And so you might actually have multiple analyses on the same region requirement being done inside of an operation. And so again, we need to disambiguate between, the parallel rendezvous happening for each of those different things, right? And so in most cases, this analysis index will always be 0, indicating there's exactly one analysis associated with this region requirement. But in some cases, if you get multiple ones, then you can, index them, and that'll help this method disambiguate across, multiple parallel rendezvous happening to check for this behavior on the same region requirement at different points. Okay, the next thing we pass in is the name of our logical region. That's not too surprising, right? This is the thing that we're going to use to do the matching to see which point tasks are going to end up effectively, aligning with each other so they can use the same collective view, right? And then we pass in the names of our instances, right? So for each of our, right, and this is an instance set because, right, different fields might be matching to different physical instances, right? And so we're going to need to do those matches for each of those fields separately. So we still need to see all the instances for individual fields that are being used, so we can do the matches, based on those logical regions and make the right collective views, right? And this is the context that this analysis is being done in, right? It's where we're ultimately going to check to see, once we've actually done this rendezvous, right, and done the matching, then that's what's actually we're going to talk to try and either find an existing collective view that names all those instances, or make a new one if it doesn't already exist. Okay, and then this is where we're going to store our output. So these are the output parameters that are going to come back from this, and I'm not going to go through all of these at the moment, because effectively there's going to be some of them will only make sense when we look at some downstream code from here. But I guess the important one that is actually going to come out of this, right, is this this collective mapping. Data structure will tell us where all the nodes are for the collective view, and we'll know whether we're the first local point on a particular node to be accessing that collective view. That'll be helpful. This thing is actually the actual names of the collective views themselves, right? And effectively, this vector will always have the same size as this target's instance set, right? So however many input instances you pass in, you'll get an entry for each one of these, right? And you'll get corresponding collective views for each of the fields, for each of those instances, saying how they align with each of these input instances that you passed in this instance set. So the size of this vector always matches the size of this target's here. And this thing we'll talk about a little later because it'll get a little complex. One important thing to note here is that this method actually executes asynchronously, right? It will give you back a runtime event telling you when all of these parameters have been filled in, but they're not safe to use until this RT event that gets passed back as the return value is actually triggered, right? And you can actually see that mattering up here in this back here. This is in the region tree, right? In this physical perform updates. Right, you can see that convert views also returns an RT view, right? That effectively says when those views are actually ready, and then that's a precondition into doing like the next stage of the physical analysis, right? Effectively passing in this views ready parameter here to say you can't actually start this traversal until these views are actually ready and so forth. And so like the little mini pipeline that exists on a physical, this is part of like the mini pipeline that exists on a physical analysis. And so, that's important to keep in mind is that this is going to execute, let's see, where did legionops.h go? Yep, this is going to execute asynchronously and do this parallel rendezvous for each of the point tasks in parallel, right? And once you've got your views ready, then you can proceed with the next stage of the pipeline. Okay, so let's actually go take a look at this method just in a little bit of detail to give you some flavor for how it works. There are some nuances to this, and you'll notice this is a virtual method. You might be wondering why that is. We don't usually want our derivative classes to be overloading this, but there is an overload for this particular collective view creator class for control application, which is the REPL collective view creator, which will be able to do the same thing, but for things operating in a control applicated context. And so there is an overload for this method, effectively for control application. But in general, if you're not control applicated, then in general we don't overload this method. Okay, let's actually go take a look at convert collective views. Here we go. Okay, so what we're gonna do is effectively, this collective view creator class, right, is actually gonna be pretty simple. Imagine you've got remember, let's handle the simple case, tying it back to this particular index-based task launch here, right? So remember that effectively the collective view creator class was inherited from by the multitask case. So in that case, the multitask is actually like the index-based task launch that owns all of these point tasks, right? So we'll just handle the case where all these points are made on a single node for now, and just assume that the collective view creator class is actually the index-based task op, right? That actually represents all of these point tasks, right? So effectively, each of these point tasks, are going to come back to this index-based to their owner index-based task operation and ask it to do this parallel rendezvous, this convert collective views method here, right? And so what this does, right, is effectively, it's going to make one of these. It's going to do this find or create parallel rendezvous. So we're going to make an object, this rendezvous result object, right? And we're going to make exactly one of those for each one of these, index analyses pairs. Okay. In fact, let's actually look at find or create rendezvous here. So we're making an object that's going to effectively help us do this rendezvous, right? And actually, I can show you here. So actually, the key, to finding these rendezvous is actually a triple, right? It's the region requirement index, the analysis, number for that particular region requirement, and then the name of the logical region that we're actually going to do that rendezvous for, right? So we're going to find this is effectively going to perform the result, for actually making the particular collective view for the point tasks that actually align with the same region requirement. But then we're going to store that effectively we'll make one of these results if we don't find one already, like on this local node, and then we're going to actually do the rendezvous across all the points in the index-based task launch. And once we know that all the points have arrived, then we can take each of these rendezvous results and make the actual collective instance or collective views and actually send the results back to each of the point tasks. Okay, so that was not the clearest explanation of that. So please stop me and ask questions if it was confusing. But I'll try and plow ahead here. Right, so we're going to make one of these pending rendezvous keys, which is one of the triples of the three things that we can match on. Right, we have some data structure actually indexes based on this key. Right. And effectively, we're going to check to see if any of the existing ones that we already have for this particular key already match the set of instances that we need. If not, we're going to go ahead and make one. Otherwise, if we find that one already matches, we can add our the set of outputs that we're going to need to update to that result, and then we return it. And there's some reference counting going on here just to make sure we keep this result alive, until everyone is done using it. But this is all local reference counting. This is all very, very simple. So you don't need to worry too much about distributed reference counting. These are all local data structures. So you don't need to worry too much about the distributed collectible stuff that we talked about before. Okay, so we make one of these rendezvous results. Let's actually look at what a rendezvous result is before I charge ahead here. Let's see. Here we go. So this is our rendezvous result class, right? So actually, this is going to be, effectively something that's going to make some collective views whenever we need to actually be able to do this. And this is actually if you look at which class we're in here, this is actually in the base class for collective view creator, right? We didn't want to duplicate all this stuff across all the instantiations of the template, create a bunch of additional symbols and stuff like that. Where'd it go? So effectively, all of this is inside our subclasses inside of that particular parent class, right? But effectively, we can see the object doing the owner of this rendezvous. We have the owner context, right? We have our key that we're associated with, right? These are actually going to be the instances that are going to be that we're going to be matching for this particular point task, right? And we got an event that represents when we're ready. And we have a list of all the things we need to update once we actually get our results, right? And if we have multiple point tasks that are using all the same physical instances as inputs, right, then we might actually have multiple entries in each of these vectors that we can update the same points, with the same collective views and stuff for all those cases. Okay, so we did that find or create rendezvous call, and that effectively deduplicates across multiple point tasks that are using the same physical instances. Right, and now we need to actually do this rendezvous mapping, between all the point tasks inside of the index-based task launch. So we've got our local result for our particular point. We now add our point to the list of data structures that are effectively trying to do this parallel rendezvous across all the point tasks in this index-based task launch. Right, so we do this rendezvous collective mapping call, which is actually right here immediately below us. Right, and so this one, this key is totally on the region requirement index and the analysis index, right? So it's just a tuple here, or a two tuple here to effectively be able to check for all the point tasks inside this index-based task. We know which region requirement we're doing this for, and for which analysis for that region requirement we're doing this parallel rendezvous for. Okay. So this collective view creator has a list of these pending collectibles. It indexes by this rendezvous key here, right? And effectively, it gets the set of existing. We have a pending collective data structure here that's going to track how many points we've seen for this particular rendezvous. If we don't have one yet, we go ahead and make one, and we ask, the parent index space task, how many points are we expecting to see, right? And in this particular case, like there would be 4 points, right? We'd be needing to see rendezvous we need to see all the point tasks arrive here with the name of their logical region so we can actually do the match correctly to actually be able to see, that we've seen all the point tasks inside of this index space task launch. Okay, so once we've got this, right, we can effectively go and add ourselves to the list of rendezvous, right? Check to see if we've already got ourselves in this vector, right? This also has an address space ID associated with it because you can get rendezvous results from remote nodes. But for the case we're talking about right now, just to keep things simple, you can assume that all these pointers, come from the same node. But there are cases where you can get pointers here, coming from other nodes, and we have to deduplicate across that, right? So that's why this is a pair of address space ID and rendezvous result pointers. Right, and so we effectively, go through here, see if we've already found one of these rendezvous results has already arrived. If it matches right on the same address space, same pointer, right, then we found it, and we can record ourselves. Right, otherwise we need to add ourselves to the back of the list. Right, and now we go through and effectively check to see if we've had all of the points actually arrive for this particular rendezvous. Right. Actually, is that what's happening here? No, that's actually happening down here. So I should describe what's happening here. So what is happening here is effectively as we arrived, right, we actually record all the instances that are being used by each of these logical regions. And this is going to help us actually make the collective views at the end of this rendezvous, right? I'm actually going to skip this part because I think it's actually not particularly relevant at this very moment, but we're going to come back to this part a little bit later. Effectively, this is grouping all the instances based on their fields to find all the fields that are aligned on the same instances for the collective view, right? Because each of again, this is a simple example where there's only one field for each of these logical regions, but in cases where you might have multiple fields, right, then you have to group based on fields and instance IDs. And effectively, this is doing that grouping eagerly here. The important part that is probably relevant, the most relevant to us right here is this part right here. Right, effectively checking to see, have we seen all the point tasks do their arrival here, right? And we better not have seen, we better still have some count available here. And we remove our count, and if it's gone to 0, right, then we can actually say, okay, we're now ready to do the matching to actually construct the collective views and stuff like that. And so, when the first point arrives, right, we're not going to be done yet, but by the time the last point does, then we're ready to do this construct. And so we can swap out the list of the rendezvous results that we've actually, accumulated, and we can actually do this construct collective mapping API call once we've got all of our point tasks that have arrived. Okay. So let's actually talk about this construct collective mapping, because effectively at this point, we've gotten all of our point tasks to arrive, in our parent index-based task launch and say, here's my regions that I'm using and here's the instances that I'm using and stuff. And now we can actually do this matching to see which points are using the same logical regions and actually make the collective views for each of these point tasks. Okay, and that happens in this construct collective mapping call. Okay. And you can see the parameters here, right? This is our rendezvous key, our region requirement, analysis index pair, right? It says, which one we're doing this for, right? And we've got this sort of map that we've constructed here of, effectively for each logical region, we get all of the collective rendezvous associated with that particular logical region, right? So we can actually go and make the, the actual collective views for that particular matching case. So effectively, we can actually iterate over each of these cases, right? So for each region requirement, right, we found all of so for each of these logical regions, right, R0 or R1 over here, right, we're going to iterate over each of those, right, and actually try to make the collective rendezvous for each of these, or make the collective view for each of those logical regions. Right. So let's see. There's some more field wonkiness here that's happening. Because again, this is the case where you might have if I really want to explain, I would have to make this example a little bit more complicated, right? Maybe maybe this P0 was reducing to R0 for field A on instance X, and field Y, or sorry, field B on instance Y, right? And then this P is like also reducing to field A on instance X, but then it's reducing to field B on instance Z or something like that. And so like you would make different collective views for each of the different fields, even though they're using the same logical region. So that's, I'd have to make this example a bit more complicated in order to actually show what some of this code is doing here for the various different fields. In this particular case, I'm going to try and gloss over the fact that there can be multiple fields happening here and try and describe what's happening, just for the cases where like there's just one field for each of these region requirements. In the case where there is exactly like one, so effectively this grouping here effectively sorts into field sets, or sorts into fields that all have the same, the same sets of collective instances. So let's see. We're really diving into the weeds here, and I probably should have thought through how to explain this a little better with maybe a slightly more complicated example. But effectively, there are two cases here, right? Once we've grouped on fields, right, we've got the names of the physical instances. These distributed IDs are effectively the names of the physical instances for this logical region up here that is shared across all the points in this particular collective rendezvous, and it's shared across all the fields, for those region requirements. And in this particular case, there are multiple of them, right? And that's the case where we can actually ask our local enclosing parent context to actually go either find or create a collective view to represent exactly those sets of instances associated with these particular physical instances that are being grouped together for this index-based task launch. There's a special derivative case down here where there's exactly one instance, and so what you've got there is like multiple point tasks actually sharing the same physical instance, but they're all sharing exactly one physical instance for the same logical region. That's pretty unusual, but it does happen. So it's just something to be a little bit aware of. But effectively, this is the common case where we're actually calling this method to find or create collective views, and each parent task effectively tracks in the case where you've got multiple of these, index-based task launches using, the same regions over and over and over again, right? We don't make new collective views every time we do a parallel rendezvous, right? Effectively, if we're constantly like having the same index-based tasks matching on the same logical regions and using the same physical instances and they're mapping over and over again, they'll get the same collective views every time across your the same parent task. So like, that's the reason that there's this like find or create collective view call here, which will actually try and make it'll find or create collective views associated with each of the or I should say it'll make it across, like it'll deduplicate across multiple index-based task launches and stuff, making these collective views. Okay, so once we've gone through and done this, effectively we do this for all the regions, for all the field sets that get made. Once we've done that, we can then send the results back out to each of these rendezvous, for each of the rendezvous results associated with like one of these, these new collective views that we've made. We can send those results back out to them, right, and tell them the results that we've like effectively fill in the collective view and all the data structures that they needed, when they made that rendezvous result, right? So these vectors of target mappings and first locals, right? We need to effectively tell each of the things in this rendezvous result, they're the actual results here, and then we can trigger this ready event to effectively say, hey, we've filled in your results, so you're actually good to go and can actually like start using your data structures. And so effectively what this does is it actually like makes those results. Effectively we're creating the collective mapping. We're determining the owners, and then we're actually sending out the results. And the sending out the results actually gets done in this finalize collective mapping call here. Let's actually take a look at that. Yeah, this is in the base class of collective view creator, right? So effectively it's part of collective view creator, right? And you can see like there's actually two paths here. There's one where the results, like your rendezvous result that you're sending this to, right, is actually on a remote node from where you are, in which case you've got to like serialize up all these results and send a message over there to actually go do that, right? Or, in the case that we're probably talking about here today, right, we're going to be on the local node, right? So effectively, you can just go through, each of these data structures and actually populate them with the right results, and tell them the results of the mapping and the views and all the stuff that they need. There's a little bit of extra stuff here for counting local analyses. Again, we're going to encounter that when we actually want to look at like how physical analysis gets done for collective views. But that's sort of a little detail beyond what we need to discuss today. And actually, if we look at finalized rendezvous here, just to close the loop, let's see. Right, effectively, it's filling in these data structures. Effectively, it's populating these data structures right here in this rendezvous result object here with all the results that we needed for ourselves, and then we can effectively trigger the ready event down here, marking once it's done. And so when that's done, right, that effectively is what unblocks like that's what unblocks this perform traversal method here. Once all these views have been converted and done this parallel rendezvous, and that effectively finishes this stage, right? So at the point where you've actually done this parallel rendezvous, made all your collective views, and then told your physical analyses like, hey, we've updated all of your analyses, right? Then you're good to move on to the next stage, which is actually to go talk to each of these equivalent sets. Let's actually do this next part before the end of the hour, because this part is actually much simpler than this parallel rendezvous. This parallel rendezvous is probably one of the more complicated parts of collective views, because it involves matching on points and region requirements and fields and stuff all at the same time to find how to make collective views. So the rest of this is actually going to get considerably simpler once we get to some of these other parts. Okay, so let's actually take a look at how each of these analyses decide which equivalent sets they go look at. Right, so when you actually do this perform traversal method here, let's actually take a look at that in the physical analysis. Where is here we go. Right, and so you can actually see there's this is a collective copy fill analysis. And if we actually look at the type hierarchy for update analysis, or for physical analysis, collective copy fill analysis, you can see collective copy fill analysis actually inherits from registration analysis. And if we actually looked at the update analysis, right, you can see this actually inherits from collective copy fill analysis, right? So the update analysis that we're looking at here is actually a kind of collective copy fill analysis. There are other kinds, other things like overwrite analysis also inherits from collective copy fill analysis, I think. But effectively, what this collective copy fill analysis is doing is effectively it's providing support for determining, in the case where we actually have some collective analysis, where we know that we've got multiple region requirements for different point tasks, all cooperating, to do an analysis for a collective view, right? We can actually deduplicate some of these analyses across equivalent sets, right? So one point might analyze a subset of the equivalent sets, and another point might analyze a different subset of those equivalent sets, right, for the same collective view, right? So that way, each collective view touches each one of the, for region R0, touches, each one of the equivalent sets exactly one time. And that allows, if you have a large number of point tasks that are all using the same logical region, that will significantly reduce the number of times that those equivalent sets need to be accessed to do this analysis. So effectively, this collective copy fill analysis is effectively a base class that helps figure out how to make that work. So let's go back to collective copy fill analysis here. And the important thing that you actually see was that this actually overloads this perform traversal method, right? And that's how it's going to effectively hook in and be able to deduplicate this for cases where we actually have some collective behavior, right? So effectively, just like normal, if there's a precondition here, we've got to defer ourselves. That's pretty standard across all the physical analysis pipeline stages. But then, what we're going to do is we're going to iterate over our target views. Right? These are the views that we made as part of that parallel rendezvous. And we're going to check to see which ones are collective. right? As a result of that that parallel rendezvous that we did before, we're going to see which of our views, for each of our managers is actually a collective view. If it's not a collective view, well then great, like we can just skip this and we can just go ahead and eventually we'll get down here and perform our traversal straight through for ourselves, right? Just like normal, right? And that'll actually just like go talk to all of the normal equivalent sets, right, for this physical analysis and do the normal thing that we've talked about in previous lessons. But in cases where this is a collective view, right, now we can effectively determine whether or not we are whether or not we should actually go ahead and do the collective analysis for this particular equivalent set, right? And effectively that's, well, actually I should say, actually that's not quite what's happening here. Let's see. So this is actually something else. I'm misleading you just slightly. Let's see. Actually, this registered collective analysis might actually do this. I am trying to page all this stuff back in. Let's take a look at Legion views. Where did Legion views go? Okay, that is not quite what's happening. I might need to defer this to the next lecture in order to remind myself exactly how we do this deduplication across the various analyses, so that each one of like these point tasks or each one of the equivalent sets gets touched by one of these point tasks analyses for each collective view. Yeah, I think I am going to stop here and make sure I can tell you correctly how this works for the next time. So this is a very confusing lecture, I realize. Collective views are one of the more complicated parts of the physical analysis. What questions can I answer for you guys in the remaining time today before I dive into anything else next time? No questions. I must have lost everybody. Okay, if I'm not going to get questions, I'm going to wrap up here today. I'm going to try to get a realm lecture for next time. But yeah, we'll try to continue the collective analysis, and I will give you the right answer for how we actually do this stage of the collective views the next time. So with that, I'll stop the recording. If you think of questions offline, feel free to shoot them to me. Okay.